आज हम डिस्कस करेंगे थर्मोडायनामिक्स इन रियल गैस पार्ट 3। द टॉपिक ऑफ डिस्कशन इज एनर्जी कंजर्वेशन के बारे में बात करना है फॉर रियल गैस, वर्क हेड इन कंप्रेसर, इंथाल्पी चेंज इन कंप्रेसर एंड प्रोसेस टरबाइन, एंड देन नोजल एंड डिफ्यूजर्स इंथाल्पी चेंज क्या होता है उसके बारे में डिस्कस करेंगे एंड स्लाइटली ऑन बॉयलर एंड हीट एक्सचेंजर। एनर्जी कंजर्वेशन इन रियल गैस, तो suppose there are 2 points of any turbo machinery. So total energy at one point is the same as another point provided losses is not considered or neglected. तो इन रियल केस में जो एनर्जी का क्या क्या है उसको हम देखते हैं। जैसे कि इन रियल केस में इंथाल्पी जो वन एनर्जी, काइनेटिक एनर्जी इज एनर्जी, देन एलिवेशन हेड इज एनर्जी। तो summation of enthalpy at one point, kinetic energy and elevation energy is the same as enthalpy summation of enthalpy at energy at point number 2, kinetic energy at point number 2 and elevation energy at point number 2 is the same provided losses are neglected. This is as per Bernoulli's equation of energy. Now this is a turbo machinery, and now we are discussing about the how we can use the this energy equation for turbo machinery. So inlet of turbo machinery is considered, let's say, inlet point, and outlet of turbo machinery is considered as a outlet point. Since elevation head is almost same for turbo machinery, inlet and outlet, so elevation head is not considered. So now we have to consider only two things. One is a enthalpy and another is a kinetic or velocity head. So how we can use thermodynamics basic principle of energy conservation? One is the Q, which is heat transfer. Another is W, is a work head. So Q minus W is equal to change in energy. So you can write H2 minus H1 plus 0.5 into bracket start V2 square minus V1 square, bracket close, where Q in heat transfer in joule per kg, W is a work output in joule per kg, small h1 and h2 are enthalpy at inlet and outlet in joule per kg, and V1 and V2 are velocity at inlet and outlet in meter per second. Now work head rise in compressor. So we call it as a work head rise or compressor work head. So work head rise occurs in compressor, which is expressed as isothermal head, isentropic head, and polytropic head. In industry, isothermal head is normally not used. Only isentropic and polytropic head are used. However, isothermal head कैसे निकालते हैं? HI is equal to Z1 into R by M into T1 into log of P2 upon P1. तो इस तरह से हम isothermal head निकालेंगे। Isentropic head का है HS is equal to Z1 into R by M into K upon bracket start K minus 1 bracket close into T1 into bracket start P2 upon P1 to the power K minus 1 bracket close upon K minus 1. Similarly, polytropic head HP is equal to Z1 into R upon M into N upon N bracket start N minus 1 bracket close into T1 into bracket start P2 upon P1 to the power bracket start N minus 1 bracket close upon N minus 1, where N क्या है? Polytropic index N is equal to log of P2 upon P1 upon log of RD2 upon RD1. RD2 RD1 क्या है? ये density at inlet and outlet condition. तो where H1, HS and HP क्या है? Isothermal head, isentropic head and polytropic head. In head rise you can say in joule per kg. P1, P2 in inlet outlet pressure in Pascal absolute. RD1 and RD2 are inlet outlet density in kg per meter cube. K is average specific heat capacity ratio in constant. N क्या है polytropic index constant. T1 is inlet temperature in degree Kelvin. Z1 is inlet compressibility factor in constant. M is molecular weight in kg per kilomole, and R is universal gas constant joule per kilomole per Kelvin. Compressor actual enthalpy rise. Abhi since compressor actual static enthalpy rise is a difference of outlet enthalpy and inlet enthalpy, which is expressed as actual enthalpy HA is equal to a small h2 minus a small h1. But it has a relation with a specific heat capacity at constant pressure, inlet temperature and outlet temperature. So we can write actual enthalpy rise H is equal to CPA into bracket start T2 minus T1 bracket close. Actual stagnation enthalpy rise is a static enthalpy rise and velocity head. So actual enthalpy rise, which is stagnation form, HAO is equal to H2 minus H1 plus 0.5 into bracket start V2 square minus V1 square bracket close. This can be also written in CP form. So HAO is equal to, it is stagnation. This is actual stagnation enthalpy rise. HAO is equal to CPA into bracket start T2 minus T1 bracket close plus 0.5 into bracket start V2 square minus V1 square bracket close. In stagnation form में भी लिख सकते हैं HAO is equal to H2O minus H1O. O represents stagnation condition, where HA and HAO क्या है static and stagnation. Actual enthalpy rise in joule per kg. A small H1 and H2 is a static inlet and outlet enthalpy joule per kg, and a small H1O and H2O क्या है stagnation inlet and outlet enthalpy joule per kg. T1 T2 in static inlet outlet temperature in degree Kelvin. V1 V2 inlet outlet velocity in meter per second. CPA is average a specific heat capacity at constant pressure in joule per kg per Kelvin. Enthalpy drop in process turbine. So static enthalpy drop in process turbine is a difference between inlet enthalpy and outlet enthalpy, which is expressed as a static enthalpy drop in process turbine H is equal to H small h1 minus h2, and stagnation फॉर्म में लिखना है तो static plus velocity head ऐड कर देना है, तो we can write stagnation enthalpy drop is HO is equal to h1 minus h2 plus 0.5 into bracket start v1 square minus v2 square bracket close. और stagnation form में लिख सकते हैं HO is equal to small h1o minus h2o. So H and HO क्या है static and stagnation enthalpy drop in joule per kg. A small h1 h2 static inlet out enthalpy, and a small h1o and h2o is stagnation in the inlet and outlet enthalpy. V1 and V2 inlet outlet velocity in meter per second. Nozzle and diffuser, although in isenthalpic process occurs in nozzle and diffuser, and so stagnation enthalpy at inlet and outlet are same, but static enthalpy drops in nozzle due to increase in velocity at nozzle outlet, and static enthalpy increases in diffuser due to decrease in velocity at diffuser outlet. The static enthalpy drop in nozzle, we can write H nozzle is equal to H1 minus H2 is equal to 0.5 into P2 square minus V1 square, and a static enthalpy rise in diffuser H diffuser is equal to H2 minus H1 is equal to 0.5 into V1 square minus V2 square bracket close, where H nozzle static enthalpy drop in nozzle joule per kg, and H diffuser is equal to static enthalpy rise in diffuser in joule per kg, a small h1 h2 inlet outlet enthalpy, and v1 v2 inlet outlet velocity in meter per second. Heat exchanger and boiler. Constant pressure process occurs in heat exchanger and boiler. In heat exchanger, heat is added to one fluid and removed from another fluid. So enthalpy increases when heat is added and decreases when heat is removed. So Heat energy exchange is equal to change in enthalpy. So heat transfer Q is equal to H2 minus H1, where Q is heat transfer in joule per kg, and a small H1 H2 are enthalpy at inlet and outlets. So thank you for watching.